Do you want to learn about special relativity? Well, you came to the right place. Special relativity, published and discovered by Albert Einstein in 1905, is the basis for modern-day physics. To understand special relativity, you first must understand two principles from Albert Einstein himself. The first principle is if two objects exist in space, it is impossible to tell which one is still, which one's moving, or if they're both moving. For instance, if you have these two rocket ships right here, and they're moving towards each other, it can just as easily be said from the point of view of this dude that this rocket ship is moving towards him at a faster rate. Same thing with him. He could say that this rocket ship is moving towards him at a faster rate, or an outside observer could say they're both moving towards each other. So this means that speed of movement must be dependent on who is observing it. So we have a little example here. Say this dude is on a moving platform and he's tossing a ball up in the air. It goes up and comes back down, just as it would if you were standing on still earth. Well, for him, the ball is only moving up 1 meter and down 1 meter, so the total movement of the ball is 2 meters, right? But what if an observer, this little girl right here, watches him on the moving platform? Well, if he throws it up, it has an arc to it because he has a horizontal component. Whereas right here, for him, he doesn't see his horizontal component because he is also moving. So this means that relative to him, the ball is moving a shorter distance. But relative to an outside observer, the ball is moving a larger distance. And the ball is also going faster because we're taking into account his horizontal component. So this makes sense, right? We can understand this. But then Albert Einstein comes out and hits us with the second principle. Although an object's speed is relative to the observer, the speed of light, c, is constant for any observer. Now the speed of light, for old time's sake, is just about 300,000 kilometers per second. So let's put this into perspective. So let's say we have the Millennium Falcon right here, and we have Chewbacca right here. The Millennium Falcon's moving towards this laser pointer, and Chewbacca's staying still. So to Chewbacca, of course, the light coming at him, he would detect as 300,000 kilometers per second. But Han Solo on the Millennium Falcon, the light speed should be faster, shouldn't it? Because like we said, if they're coming together, then that means it must be his speed plus light. Well, no, because we're looking at here, this to Han Solo is also 300,000 kilometers per second, because light is constant to any observer. Okay, well, if you think about this very hard, it presents a paradox. This paradox goes like this. So let's say we have two mirrors right here. They're parallel to each other. And we have a laser pointer at the top end of one mirror. Mirror 1 is staying still. Okay? So the laser pointer shoots down a laser beam, reflects, and goes back up, as you can see right here. Down and up. The total distance traveled by this laser would be twice the length between the two mirrors. Okay, so what if we do the same thing that we did with the moving platform? What if we get these mirrors right here and we push them to almost the speed of light, very fast? And now this set of mirrors right here, mirror 2, we can see that this would be the path traveled by the light. So let's say we time them and we move them. Well, theoretically, it should take the same amount of time, right? For this laser to reflect off this surface and come back, this laser to reflect off this surface and come back, right? But how does this laser right here travel a larger distance than this laser right here? Well, Einstein thought about this. And what he said is that since the speed of light must be the same, that there must be something else compensating for this extra distance coming from the light at mirror 2. And he said this must be time dilation. Now what time dilation is it's basically saying if an object is moving, then time slows down. Now it's hardly noticeable, especially for practical uses. But if you're moving very fast, like this mirror 2, moving almost the speed of light, then it can be noticed and actually has an effect on light. So time must slow down, and since the moving mirror has more time, that means it has more time for the light to travel a farther distance. Now this doesn't make any sense, right? Surely this is just some old German dude not knowing what he's talking about. Well, not really. We've done experiments on this. The Halfwell-Keating experiment proved this. What they did is they sent 4 atomic clocks, and atomic clocks are very accurate clocks that can detect even the smallest fraction of a second. And they put them aboard commercial airliners. And they sent these airliners out. And the airliners went around the world twice, different speeds, whatnot. And the airliners came back to the naval base. And these atomic clocks were then compared amongst all of the airplanes. And they actually found that there were a difference in them. Now the spooky part is these differences coincided exactly with Einstein's equations for time dilation. Well, mark it up. Another win for Einstein. Thank you.
We're going on a trip in our favorite rocket ship, zooming through the sky, little Einstein.
Oh, hello there. My topic today for this presentation is every man's worst fear, length contraction. Now you might be wondering, what is length contraction? And that's a very just question. But I'll start with reading you a nice definition here. The length of an object in a moving frame will appear to be shortened in the direction of motion when traveling close to the speed of light. Now, I'm going to start off with an example shown out on this paper over here. So, first things first, perspectives are everything when it comes to comparing the different traits of special relativity. But the first things first, you start off observing as this person on Earth. If you see a rocket traveling by at 99% the speed of light, it'll be a blip. It'll go so quick you won't be able to see it. But if you look closely, it'll appear much smaller than it actually is. Now moving over to the example of the person in the rocket, if you're sitting in the rocket, your ship will appear to have the same length as if you were to stand not in motion. But when you're flying past Earth moving 99% of the speed of light, it'll appear that your rocket isn't moving at all, but that Earth is smaller and Earth is moving away from you at 99% of the speed of light. Why this might be? Well, observe the Lorentz transformation equations. Now, you've got c, which is the speed of light, which is 186,282 miles per second. And you're probably just like I am. Wow, that's fast. But you see this value of L naught? L naught's the initial length of whatever you're measuring. So, say in this example over here, L naught is the initial length of this car. This is when it's not in motion, it's stationary. But you come back over to this equation, V is the velocity you're traveling at. The closer you get to the value of C, the smaller the decimal you'll get within this square root. And when you take the square root of a small decimal, you'll get an even smaller value, which you then multiply by the length, which means the faster you move, the shorter the length of the object is going to be. So you come look over this example here. You have one car moving at 8.8796 times the speed of light. You can tell that from its initial value, it shrank quite a bit. When you observe this bottom car here, it's traveling at 0.9996 times the speed of light. That means that this value here almost comes out to being 1, which would mean that 1 minus 0.999 whatever is going to end up generating such a small decimal that you multiply the initial length by, which would result in the final length being a very small value. And you can come over here and observe this rocket ship example again. You have L as the initial length, or L naught as the initial length for the rocket. When you take this L naught and you say that the velocity is 99% the speed of light, this would generate an L value much smaller than the L naught you started with. Well, that seems hard to follow, and conceptually it's not very logical, but mathematically it makes perfect sense. This equation is what justifies the way things work in this universe. And in closing, I'd like to lead it over to Brendan.
We're going on a trip in our favorite rocket ship, zooming through the sky. Little Einstein.
Thank you, Chris. Now let's move on to a topic that most men don't fear: mass increase. What is mass increase, or more commonly known as relativistic mass? Well, to understand this topic, we must first understand what mass is. Chances are, throughout your childhood education, you were told that mass is the number of atoms in an object. While this isn't wrong, it's not the most accurate statement either. Well, what your childhood professor was describing to you is what Einstein would call rest mass. But we'll get a little on that later. So if this isn't what mass is, then what is it? Well, mass is energy. This is the basis of Einstein's equation E = mc squared. Mass can also be defined as the resistance to acceleration. One simple example comes to mind when trying to piece these two concepts together. Take a box of a certain mass, right? We're going to move it up against Earth's gravitational acceleration. We know when we do that, the box resists the acceleration. What's also interesting is when the box moves upward, there's a gain in potential energy. So if mass is energy, and you add energy to the box, then you're adding mass to the box, right? Well, yes. That's exactly what Einstein's equation tells us. If there's an increase in energy, there must be an increase on the other side of the equation too. And we know, as Chris and Paul both told us, c, which is the speed of light, is constant. So if you increase energy and you have to increase the other side of the equation, the only thing that can change is mass. Let's take another example. Take a spring. We know that when you stretch a spring, then there's a gain in potential energy, as we know. So if we increase the energy, we know speed of light is constant, then there must be an increase in mass. All right, let's move on to our last example. Let's take an object, in our case a box, of a certain mass. Forget this for a second. This box isn't moving. It's at a rest mass. All right. When an object is at rest, it has rest mass. Okay, take this object, this box, and we're gonna move it faster and faster, gaining more and more kinetic energy. You would gain increasingly more energy, or mass. More energy, more mass. Now you may be wondering, how much does this mass increase? But don't worry, Einstein's got you. He created an equation to determine exactly how much the mass increases, and it's shown here, where m naught is the rest mass, v is the velocity that the object is moving, and c, of course, is the speed of light. So if I were to sum all of this up, I would tell you that the mass is energy, and it's also the resistance to acceleration. The more energy in an object, or the more you increase the energy, the more you increase the mass. It may be interesting to note that while Einstein initially used the concept of relativistic mass, he later regretted it and insisted that only rest mass should be used. In all of his other later works, he only uses rest mass. Interesting. This concludes our project. Thank you.